Hi, Mrs. Durasset here. Today we're taking a look at section 3.31. We are going to be using critical numbers and the first derivative test to find relative extrema. So we're going to start off by looking at this first example. And it says we want to identify the open intervals on which the function is increasing or decreasing. Well, if I look at this function and you see where I'm tracing over top of it, as I go from negative infinity to -1, that function is decreasing. As I go from -1 to this x value right here, which is 0, so from -1 to 0, the function is increasing. Then right here, from an x value of 0, and again, we always use the x's, not the y's. So as we go from 0 to 1, the function is decreasing again. And then as we go from 1 to infinity, the function is increasing again. Now, I want to point out something very important. I'm not putting infinity because this function's going way up. I'm using infinity because it's going way over, okay? That's not really easy to see that we keep going over and over, but we do. See, these are x values. And I can also see that when that function goes from decreasing to increasing, see how we're going from decreasing to increasing? What do we get right there? We have a relative min, don't we? So whenever our function goes decrease to increase, we're going to have a relative min. Then our function went from increase to decrease. When we go from increase to decrease, we got a high point, so we had a relative max. And then we went from decrease to increase, and what do we have right there? Decrease to increase. We have a relative min again. Okay, so that's going to be something important to keep in mind when we do this first derivative test that we're going to be looking at. Okay, so in our second example here, it says find the critical numbers, if any, and to find the open intervals on which the function is increasing or decreasing, and to locate all relative extrema. Use a graphing calculator to confirm your results. We want to remember what critical numbers are. Critical numbers are the x-coordinates of possible relative maximums or relative minimums of a function. To find critical numbers, the first thing we always want to do is find vertical asymptotes. We do this by finding the values of x that make the function undefined. Vertical asymptotes are not going to be critical numbers. The reason is the function isn't even defined there, so it definitely can't be a high or low point if we don't even have the function there. Step 2, set the first derivative equal to 0 and solve. These x values are CNs, critical numbers. Find where the first derivative is undefined. These are critical numbers unless they were also vertical asymptotes. To find extrema using the first derivative test, we're going to make a chart. We're going to put vertical asymptotes into the chart as well as critical numbers, and then we're just going to look at whether the function is increasing or decreasing on each interval. All right, so looking at this first problem, before I take the derivative, I'm going to go ahead and rewrite the problem. I'm going to distribute. So that's going to give me negative x squared minus 8x minus 12. Now I'm going to have to take that derivative, and that derivative is going to be negative 2x minus 8. Now we have to set that equal to 0. Negative 2x minus 8 equals 0. Bring the 8 over. 8 equals negative 2x, and so x equals negative 4 is going to be the critical number. So now I'm going to use my first derivative test with that critical number. So my first interval is going to go from an x value of negative infinity to an x value of negative 4. My next interval is going to go from that critical number of negative 4 to infinity. And that's because I only had one critical number, so that's all I needed were those two intervals. So now I have to think, what is some number in between negative infinity and negative 4? Let's choose negative 5. Negative 5 is a test value. I want to know what is the slope at negative 5. So to find that slope at negative 5, I'm going to have to plug it into this derivative right here. So negative 2 times negative 5 minus 8. I'm plugging that negative 5 into that first derivative. So that's going to give me 10 minus 8, and that's going to give me a positive answer. If I get a positive answer for the slope, that means the function has to be increasing. It has to be going up. Now I need a number in the interval from negative 4 to infinity. Well, I could do 0, right? That's in there. So now I'm going to plug 0 into that first derivative. Plug 0 in. I have negative 2 times 0, that's 0, minus 8. That's going to give me an answer of negative 8. That's a negative answer. I plugged into the first derivative. That first derivative tells me the slope. If the slope is negative, my function has to be decreasing. So here's the way my function has to look. At negative 4, I'm going to be going from increase to decrease. So I'm going to actually find out what is that answer, what is that value when x is negative 4. To find the y value, I have to go up to the very beginning. So I'm going to do negative, I'm going to have to do f of negative 4. So I can do negative 4 squared, and that's going to be, I have that negative out in front. If I do negative 4 squared, that's positive 16. Then I'm going to have to do plus 8 times negative 4, that's negative 32, and then plus 12. So just working inside of here, I'm going to have 16 plus 12 is 28. 28 minus 32 is negative 4, but I've got a negative 4, so that's going to give me a positive 4. Okay, so my point then is negative 4, positive 4. So now I can do a little sketch of this graph. Negative 4, positive 4 is this point. Until I get to negative 4, the function has to be increasing. And then once I get to negative 4, the function has to be decreasing. And that's just a quick sketch of it. Now, it also asked us to check it on our graphing calculator. Hold on. So I'm going to put that into my graphing calculator. So we're just going to go to y equals, and we're going to type that original function in. And we're going to check and make sure that we did this correctly. Okay, and here's the way it looks. Okay, if I wanted to, I could compute that maximum. I can do second, trace, calculate a maximum, and I can go to the left side of it. Go to the left side of it and hit enter. Go to the right side of it, hit enter. Hit enter one more time. And then it's going to tell me what that maximum value is. And do you see how it's going to tell me that it was at negative 4,4? So I'm checking my work there. So negative 4,4 is going to be the relative max. We could also call it an absolute max on this problem because that function doesn't have any other extrema, so it's not like it could turn up or anything. It's got to always be going down at the ends because it's a parabola. Okay, let's look at the next one real quick. So on the next one, I'm going to have to take that derivative. So I'm going to do f prime, and that's going to be 2/3 x to the negative 1/3. The derivative of negative 4 is just 0. So I'm going to simplify this, and this is going to be negative 2 over 3 cube root of x, or x to the 1/3. Now, remember, those critical numbers are going to be whatever makes this function equal 0 and whatever makes this function undefined. So when I check this, the top is never going to equal 0. So I don't have a critical number because of that. But a critical number is also whatever makes that denominator 0. So I do have a critical number. That critical number is going to be at x equals 0. Let me go back and label this as a CN. So I have a critical number there at 0. Okay? It is not a vertical asymptote. The reason why is because that function is defined at 0. If I plug 0 back into that original function, I get negative 4. If I plugged 0 in and it was undefined, then it would have been a vertical asymptote. Okay, now let's do our vertical first derivative test. So we're going to go on our intervals, negative infinity to the critical number and the critical number to infinity. A test value here would be negative 1. I plug that back into the derivative. Okay, because I want to know, is this function increasing or decreasing? That's the whole goal. So if I plug in negative 1, I'm going to have 2 over 3. The cube root of negative 1 is negative. So a positive divided by a negative is a negative. Therefore, the function has to be decreasing. Now I'm going to plug positive 1. This always goes back into the first derivative. Plugging 1 back into that first derivative, I'm going to get f prime of 1, and that's going to be 2 over 3. Cube root of 1 is 1, so 2 over 3 is a positive number. So that slope is positive, so the function has to be increasing. So now we have to do a little sketch of this. So I now want to know, what is that actual point? My function's going from decrease to increase. Think about this, guys. It's going from decrease to increase. So I'm going to have a minimum. I'm going to have a relative min at 0, comma, where do we plug back in to find a point? Back into the original function. 0 to the 2/3. That means the cube root of 0 is 0, squared is 0, minus 4 is going to be negative 4. So we're going to have a relative min at negative 4. Now, this function, this x to the 2/3 minus 4, you may not know exactly what that looks like. This is a function that we don't use a lot, but I know I have a relative min here. Now, since we don't know exactly what it looks like, we should put it into our calculator to see. So we go to y equals, and we're going to put in the function, and it was x raised to the 2/3 minus 4. So I just put that function in, and I'm going to do a zoom 6 or graph. And here's the way that function looks. Can you see that minimum there? And it's like this bird shape. I call it the bird shape, but it's actually called like a cusp. So it's going to come down like this and then shoot up. I call it the bird shape. You know how when you're young and you're making birds and they look like that? I don't know if you guys ever did that, but anyway, so this cusp shape is what we get. It comes down and then it hits that and then it comes back up. Okay, so that's what we're doing with the first derivative test. The first derivative test uses our intervals with the critical numbers, and then to find the actual point, the actual maximum or min, we have to plug that critical number back into the original function to find that actual point. Okay, I hope that helped.